How you doing? I'm Mr. Rose, and today we're going to continue discussing force and potential energy, and we're going to discuss a problem. And that problem we're going to discuss is right here, 7.36. You can see there's some calculus in it, so I'd like you to take a read at that problem. Essentially, we've got some conservative force moving some object, and that's what we're going to try and tackle today. So, the basis of the problem, I've got a textbook here open that you can't see. But the basis of our problem are telling us that we've got some potential energy function. And that potential energy is given about the x and y as alpha. And alpha is given as some positive constant times 1 over x squared plus 1 over y squared. Again, they tell me that alpha is some positive constant. So that's something that's probably going to be good to know. And they tell us in the problem that this is a conservative force. And that is a huge key in how to solve this problem, that conservative force. And essentially they want us to derive an expression for this conservative force given this potential energy function. So we know that a conservative force means I'm going to use this force is the gradient of my change in potential energy about the x and the y-axis. Obviously, technically, there should be a z-axis here, but there is no z component, so I don't care about that. As a quick review, we should recall that the gradient is a partial derivative. That's the partial derivative with respect to x in the I direction, plus the partial derivative of energy with respect to y in the j-hat direction. Sorry, that's definitely a j-hat. My potential energy then is given by that, and really all we're going to do is a direct substitution. We're going to directly sub this in for the gradient, our function in for the potential energy, and then we're going to learn or see how we actually calculate that. So this direct substitution, I should have f is equal to negative. We know there should be a negative sign there. Negative partial derivative with respect to x in the I hat plus the partial derivative with respect to y in the j hat, and then my direct substitution, alpha times 1 over x squared plus 1 over y squared. And that's it. Should be nice and simple now. Well, what we're going to do is we're going to end up distributing this stuff out. So I'm going to say that I have a force equal to negative my partial derivative of u with respect to x times alpha 1 over x squared plus 1 over y squared. And that's all in my I hat direction plus my partial derivative with respect to y of alpha times 1 over x squared plus 1 over y squared. And that's in the k-hat direction. So now that I have that, what exactly do we do here? Remember, what the heck are these partial derivatives? Well, the partial derivative means I'm going to take a partial derivative with respect to x. Here we go. There's my x. That means this y is a constant. So I want you to recall, what is the derivative with respect to x of any constant, like 2? The derivative with respect to x of 2 is just 0. So essentially, that's going to end up going away. So I'm going to deal with just the x and the y kind of separate. Separate my paper here for a moment or two. I'm going to say the force in the x direction is equal to my partial derivative, my negative du over dx. You don't really need to do this step. This is kind of redundant. Of alpha times 1 over x squared plus 1 over y squared in the I hat direction. And now what we're doing is, well, you know what? Just to simplify things, I know there's an I hat here. Bad, this is bad for me to do, but I'm just going to leave it alone. I'm going to drop it. I'm going to add it to the end. When I add it to the end, I know this is in the I hat direction. I'm keeping in vector form. I just want to have less variables as we go, so it might be a little bit clearer for you. So this is my partial derivative. Well, I'm not the best with derivatives just yet, so I'm going to rewrite this as f of x is equal to the negative partial derivative of alpha times x to the negative 2 plus y to the negative 2, because that makes it easier for me to see how to do the derivative, right? So I'm going to bring that negative 2 down. I'm going to drop that to a negative 3. So my force in the x direction, after I take my derivative, I could distribute that alpha through, I'm just keeping it on the outside, is going to be negative alpha times, this is going to be negative 2x to the negative 3 plus 0, right? That y has no derivative with respect to x. Now I'm going to put that all together. My negative times negative is a positive, so I have 2 times alpha over x cubed in the I hat direction. That is my force in the I hat direction based on this expression, my change in potential energy. The same exact thing should happen with the y. You should see that because my expression is pretty much the same. So my force in the y direction is the negative, I dropped that. Oh, that's correct up there, sorry. My negative partial derivative with respect to y of alpha times 1 over x squared plus 1 over y squared. Again, that k hat should be carried all the way through down. I can add that here now. So I am correct. I just thought again would be easier without the variables. I'll do the same thing on the other side. So now my f of y is again not the best with derivatives, so going to make it a little bit easier for us to look at. Alpha times x to the negative 2 plus y to the negative 2. And now when I take that derivative, f of y, my partial derivative is going to be alpha, the partial derivative of x to the negative 2, that's just 0, plus negative 2 y to the negative 3. That means my force in the y direction due to this change in potential energy is 2 alpha over y cubed in the k hat direction. Add my k hats back now. So now my force, because I need to add it all, right? If we remember, my force from last was the partial derivative with respect to x I hat plus partial derivative with respect to y k hat plus partial derivative with respect to z j hat. Well, there is no j, so I just need to add those guys together, which means my derived expression for force, make sure it's a vector, is 2 alpha over x cubed I plus, whoops, that guy, 2 alpha over y cubed j hat. I can pull out my 2 alpha, and I can say my general expression, 2 alpha times I over x cubed plus j hat over y cubed. And that, my friends, sorry about that, is how we figure out partial derivatives. Again, it is kind of the special derivative where anything that's not with respect to x or with respect to y or with respect to z are just constants. It's a real nice, easy expression or easy thing to do. Last time, the reason we do that is because we know energy is a scalar quantity. That's what this gradient is about. And if that gradient is about, and if energy is a scalar quantity, that means when I was moving this object, the energy in the y did not change because its position changed in the x. In this case, they both change, and they both change, it looks like the same, but one is independent essentially of the other. That's all I have for you today. I hope you could figure this problem out and solve. By all means, feel free to like, comment, or subscribe. If you have any questions, send them my way. And that's all I have for you. I need a good way to end these. I never have a good way to end these. I'm going to end it on 10 minutes in 2, 1. I missed it.